with respect to time is oh, and I forgot to point out, rho is actually, if you draw it from the horizontal here up to there, that's rho. Or said another way, if you draw it, from the tail of ut, rho would be up to there plus pi over 2, right? So the old way we defined, sorry, did I say rho? Oh yeah, okay. So phi, before we defined phi as the horizontal up to ut. That used to be phi. Now it's basically the horizontal ut. Phi is that plus pi over 2. Okay, because now it's kind of the angle of un instead of ut, the way it's drawn here. But it really doesn't matter because the derivative of phi with respect to time, whether you define it like this or our old way, it changes the same rate. It's essentially, derivative phi with respect to time is essentially the apparent angular velocity of length 3 on 2. If you're stuck on 2 like an ant and you're watching 3 rotate as it moves along its path, that angular rotational speed is phi dot, or derivative phi with respect to t. Okay? And again, whether you define phi like this or phi like that, you take the derivative, the pi over 2 goes to 0, and it's the same rate, same speed. Okay, so that in mind, if you take that, this equals d phi divided by ds times ds divided by dt, because the ds is canceled from the chain rule, right? And you're left with d phi divided by dt. So if you take 1 over rho times ds, that's the same thing as taking d phi divided by ds times ds dt. The ds is canceled, and you get this. So hopefully you can see that that is that. Okay, and remember, ds dt is s dot. It's the speed that link 3 is moving, the apparent speed that link 3 is moving on link 2. If you're stuck on link 2, that's the speed you're moving link 3 with respect to link 2. And therefore, you could call it VP3/2. It's the velocity or the speed of link 3 with respect to 2. If you're an ant sitting on 2, that is ds dt. So these are the same, so it's just divided by rho. Now that's a scalar there. Okay, so we now have to, if we want to make it phi dot bold as a vector, okay, then we have to give it delta phi dt is the magnitude, obviously, but in the b direction, ub direction, or b points perpendicular to the page or perpendicular to this. It points in the z2 direction, perpendicular to the plane of link 2. Okay, and if this is deceiving, this isn't going there, it's pointing out at you, just like ub is. So it's rotating that direction. That's a vector and a unit vector. So that's the magnitude, that's the direction. And so now instead of just doing this all scalar, we add it onto ub here. Okay? Okay, so that, at this point you're like, wow, where in the world are we going with all this? Trust me, we're going somewhere, but right now I'm just pointing out kind of random facts that we're going to use in a little bit to make a proof for this. Okay, so note that phi dot bold, the vector, is the angular velocity of link 3 with respect to link 2. It's an apparent angular velocity. And now we'll say, suppose we define omega bold, it's an angular velocity vector, to be the absolute angular velocity of link 2. Okay? So say link 2, this link, or this square here, is flipping through space, and with respect to the ground, its angular velocity is omega. That's the absolute angular velocity of link 2 is omega. But the apparent angular velocity of link 3 is, as we said, phi dot. Okay? And so you could imagine to find the absolute angular velocity of link 3, well then, you would just add them. Omega plus phi dot, whether these are both vectors, right? They're the absolute angular velocity of link 3. It's the same thing as, the apparent velocity, the linear velocity. If you're driving a truck, I throw the baseball, add the speeds of both, and you get the speed that it hits you with on the ground. You can do the same thing with angular velocity, just like linear velocity. So omega plus phi dot is the absolute angular velocity of link 3. Okay? So now, okay, but what about the rest of this equation? How do we know that if you take the derivative of u hat t, this unit vector, with respect to time, how do you know that equals the absolute angular velocity of these two velocities added together of link 3 cross ut? Well, if you recall this that we derived the derivative of RPQ, the position difference vector between P and Q on a body, equals its omega cross RPQ, which is the velocity difference vector, right? We did that huge proof in topic 2. Well, notice that RPQ, very much like a unit vector, is a vector that has a direction and magnitude, but as it flips through space, the relative position between P and Q don't ever change. Therefore, the magnitude of this vector never changes. It's always the distance between P and Q, because they're stuck on a rigid body. As it flies through space, the distance between them doesn't change. So the direction of that vector changes as it flips through space, but the magnitude stays the same. Okay, so anytime you have such a vector and you take the derivative with respect to time, it's always going to equal that it's the angular speed of that cross that vector. And you can see it as the exact same form. ut is a unit vector. It never changes magnitude. Its magnitude is always 1, but it can change its direction. So anytime you take the derivative of a unit vector that doesn't change its magnitude with respect to time, it's going to be the same thing. You just got to make sure this is the absolute velocity of that ut, which of course ut is stuck on 3. The absolute velocity of ut there, right, is this guy. So that's why you want to use this velocity. Okay. Okay, so hopefully from the past, since we proved this is true, and you know that the magnitude of RPQ, the magnitude of ut, just like RPQ, doesn't change, you can prove that this is true. Okay? Okay, so if that's true, then you can distribute this in, cross product of both, omega cross this plus phi dot that cross that. Okay, and we'll simplify that. Now remember, we proved that this dot as a vector equals that. So we're going to plug that in. So again, we just got rid of this. We're going to rewrite that as that. Plus, now we're going to plug this in there. So you get VP3/2 over rho UB. Remember, these are scalar. That's the magnitude. That's the direction cross UT. Okay, and we're going to then get rid of that and move on to the next one. What do you think some magnitude UB cross UT is? Well, remember, UB is coming out at you. If you cross it to UT, you're basically going to get the magnitude of this, and these, by the way, are perpendicular. So if you're cross-producting, take the magnitude of this times the magnitude of this, which is 1. So it's just the magnitude of this, times sine of 90 degrees, which is just this. And it's going to point in the UN direction, because UB cross UT is UN. Okay, so we could simplify this to just that plus this, where this is UN. Okay, and so we're going to remember this. We're going to remember that the derivative of ut prime with respect to time is this. Okay, I'm going to put it up there some other time, but that's one to write down and know. Okay, so we did a lot of derivation to get there. Okay, by the same token, we're going to do another similar thing where, the derivative un. Remember last time this was derivative ut with respect to time. Derivative un with respect to time is also the absolute angular velocity of length 3, right? Because un moves with ut. They're always perpendicular to each other. Okay, but cross un. So the only thing that changed from the last equation is instead of t here, these are both n's. And of course, if it's true for t, it's true for n because it's also a unit vector that doesn't change its magnitude. It's just a unit of 1. Okay, and so what we get there is, again, we distribute this in there. Get that. Okay. Then what we get, this is phi dot, which again is up here. So we're going to plug that back in. So it's very similar to what we did last time. But now when we go to this, it's a little different because we did all this with un. So what's ub cross un with this magnitude here? Well, ub cross un goes in the ut direction, but in the opposite direction. It's tangent to it, so it's negative. So you still get, again, these are both perpendicular, so magnitude of this times magnitude of 1 is nothing, times sine 90, which is nothing. So it's basically that times ut, but negative because ub cross un points in the opposite direction. Okay, so again, we're going to take this equals this, and we're going to throw it up there. So you can see here, these two equations up there, that's the ut one, that's the un one. We just proved all that. Where really the only difference here is this is a negative, that's a plus, that's un, and that's ut. Okay, so we just did some very convoluted stuff to prove that, and now we know. But you're like, well, still, why do I care? Well, you will in a minute. Okay, but right now it's not apparent where we're going here. Okay, but you'll see. Okay, so now let's take the derivative of VP3 with respect to 2. Sorry, VP3/2 with respect to time. Okay, in other words, we're going to take the derivative of this guy with respect to time. Okay, well, if we take this, where again this is a vector, you can see here this is bold. That's a vector, which is ds dt over ut. What you get is, of course, ds dt changes as a function of time, and ut changes as a function of time because that tangential vector moves. So you have to use the the product rule. Okay, and by the way, why are we doing this? So now we finally have a semblance of why we're doing this. We're after apparent acceleration, right? So it makes sense that if you want to find the apparent acceleration, that you would just take the derivative of the apparent velocity with respect to time. So this is the velocity of p3 with respect to 2. If you're an ant on 2, what's the apparent velocity of p3? Well, what we're going to do is let's take the derivative and find the acceleration, the apparent acceleration of p3 with respect to 2. That's what we're doing. Okay, I forgot to tell you that. So the derivative of this is take the normal thing there times the derivative of that from the product rule plus the derivative of that, which is the double derivative of s with respect to time, times the normal one of that. So you can see using the product rule, if I take the derivative of this with respect to time, you have these two things that are changing, so you get that. Okay. Okay, well, conveniently, we have this up here, dut over dt is right there, and we can plug that in, and you see we get this. So we have ds times all that stuff up there, okay, which, ds times all this stuff up there is here, and since there's two components, you see two ds's because it distributes in, one times the first cross product, and then the other times vp3/2 over rho, so there's ds, the first thing, ds times that, and then we leave this one be, okay, because we just plug that in there. Okay, so we took that thing in the box, plugged it in this box, and stare at it, you get this. Okay? Okay, well, let's move on to the next thing, which is, notice ds, okay, is right here. Okay, and it's basically s dot, or it's the same thing as vp3/2, right? ds dt is what the speed is of length 3 relative or with respect to 2. So if you're an ant on 2 and the 3 is moving, that's what ds dt is, which is the same thing as vp3/2. So we might as well take this, and instead of writing ds dt times vp3/2, just do vp3/2 squared. So take the speed squared divided by rho, un, okay? And then, we move ds in here, just leave omega there, and move ds in here, and if you have ds times ut, that is vp3/2 as a vector. Okay, so this is a bold omega cross a bold vp3/2 because they're both vectors, plus this is scalar, even though it looks kind of bold here. It's a scalar speed squared divided by rho. Here's the bold vector un that comes from this, and then plus ds squared, double derivative of s with respect to t, ut. Okay. Okay, so when we take the derivative of vp3 with respect to 2, or /2, we get this stuff, which kind of makes sense, okay? So you would expect the acceleration of p3, the apparent acceleration with respect to 2, so of p3, ap3/2, would have some normal component, some tangential component, some centripetal component, some tangential component. And indeed they do. Look at this. You see this is the speed, the apparent speed of p3 with respect to 2. If you're an ant on 2, that's the apparent speed squared divided by rho. That's the centripetal acceleration magnitude in the un direction. Remember, p3 is going around this curve, and at this point right there, it's basically rotating around a circle whose center is c2 with a radius of rho, so it's pointing in there. This is the centripetal apparent acceleration, or the normal apparent acceleration. And then ds, or s, double derivative, is essentially the acceleration as p3 screams along the apparent acceleration in the tangential direction ut. So that's the tangential one. Okay, so you have an acceleration that's centripetal going inward towards c2, and one along the path UT, and they're both apparent. So, with the /2 thing, see the /2, that means apparent or relative with respect to 2. There's the normal one, the tangential one adds up to this. But then you have this weird thing here. Like, you'd think if you took the derivative of this one, the apparent velocity, you would just get the apparent acceleration. But we got the apparent acceleration and the two components of the normal and tangential as we would expect, but suddenly out of the blue we get this thing as well. And the thing that's really weird about this is it has an apparent velocity vector here of 3 with respect to 2, but it's also got an absolute angular velocity term, omega. Here, remember, this is the angular velocity of link 2 as it rotates with respect to the global coordinate system, the absolute. So we really shouldn't be seeing any absolute velocities by taking the derivative of the apparent velocity, but we do. And it's in this mystery term here. And you might be like, well, what is that? Well, I'll tell you in a minute. Okay, but for now, we got what we expected, the two normal and tangential components plus a mystery by taking the derivative of the apparent velocity. Okay, and by the way, we're going to take this equation down here and we're going to put it up there with our other two. Okay, so we've done a ton of work to define these three equations that you see up there. Notice that the two are already up there, and we're just going to take this third one and move it up there. Okay, so those are the first two we defined. There's the one we just defined. Okay, so now we're going to go for the gold here. We're going to find the full apparent acceleration equation. Okay, so first of all, let's write an expression for point P3. Okay, so RP3, okay, points, something that points from the global coordinate system, right, to P3. Okay, and that is RC2, so this point, a vector that points to C2, plus negative UN rho, or just negative rho UN, right? Because remember, UN points this way. If you want a vector that points from C2 to P3, remember P3 is on 3, but it's at that point, it's coincident with P2 at this instant. Okay? And remember, this is the center of the circle that's tangent to this point, and rho is its radius of curvature, and UN is pointing in. So negative rho UN is a vector that points from C2 to that point. So if you take RC2 minus rho UN, you're going to go a vector there plus a vector there, so you're pointing to RP3. Okay, so that is a vector that points to RP3. Now, if we take the derivative of that with respect to time, we'd imagine we get the velocity of P3. Okay? All right, so if you take the derivative of this with respect to time, you have VP3. That's what you're after. This is position stuff. This is now velocity land. And here we have, if we take the derivative RC2 with respect to time, then we have the velocity of C2, so that's the velocity of this point there. Okay, and then we take the derivative of minus rho UN. Okay, well, what's the derivative of that one? Well, the derivative of rho UN, okay, is you're going to use you're going to take the derivative of this guy with respect to time, which I boxed here. Okay? Now, you might think that, listen, rho changes with time as well as UN. That was something that confused me for a very long time, because if you're taking the derivative of this, take the derivative of that and take the derivative of that, but these two things change with respect to time. Notice, if it's a circle, then rho, as the thing moves, stays the same. It's just the radius of the circle. But in this instance, as it moves, you can see this is no circle, and we want to do a general thing for any slot. So you think as that link 3 moves at different delta t, the rho is going to change. And so shouldn't you take the derivative, do the product rule of this, the derivative of this with respect to time? And the answer is no, actually, because if you think about it, as this moves to a different position at some delta t later, C2 even moves, right? Because this, you put a different circle that might have a different radius, rho, and has a different center, right? So we're just trying to get from C2 to the point, basically P2, which is below P3 initially, and C2 doesn't change and rho doesn't change either for doing that. So That's why this doesn't, you take the derivative of RC2 with respect to time, that point moves through space because 2 changes, so there's a velocity there, but it's not like C2 moves with respect to link 2, which if you move this along there, you'd imagine the center of the circle would move and the rho would change. And we're not thinking of that. That'll just confuse you, right? C2 stays fixed on there and rho stays fixed. So when you take the derivative of this with respect to time, this is constant. That changes. That's the velocity, VC2. And basically what you do is you take, just the derivative of un with respect to time and times that by rho, which is what this ends up equaling here. So see, negative, here's the negative sign here, right up there, times this by rho. You move rho into un, okay, plus, right, well, there's a negative there, but there's also a negative there. So this is plus rho's in there, and these guys cancel. Okay, and so voila, from this, these guys cancel, so you have the velocity of P3 is VC2, okay, minus omega cross rho un plus VP3 with respect to 2. So notice when this canceled, we had just the scalar times ut, which is a vector. You could either leave it like that in magnitude and direction, or you could just lump it in and have that be a bold vector. That's basically the apparent speed of v3, or velocity of vector of point 3 with respect to 2. Okay, so this should look familiar to you. This is apparently, so here was the position. If we took the derivative with respect to time, it's velocity. We're talking, this is basically the velocity difference vector, right? Because we're stepping from C2 to P2, or really P3 is what we're interested in, right? And so to do that, you take the velocity of C2 and add it to omega cross negative rho un, which is a vector that points from there to there, right? So this is the same stuff as like if this was P and this was Q. Take the velocity of Q, take the omega of cross a vector that points from there to there, and that's the velocity of P. So that's the velocity difference equation. So that's essentially what we're doing here. But imagine making that plus and putting the negative in there. So negative rho un is a vector that points from there to there. So you take omega, okay, which is, of course, the speed of the angular velocity of link 2, and you cross it by the vector that points from there to our, basically P2, okay, which is this thing right there with negative, and then and that right there is the velocity difference equation, where here's the velocity difference vector, and there's the velocity of, remember, the q plus omega rp, all this stuff is essentially getting from there to there, where that's P2. But again, P3 is coincident on top of P2, so now you have to add the velocity of P3 relative with respect to 2. This is apparent velocity equation. You take the velocity of P2 plus the apparent velocity of P3 relative with respect to 2, and you get the absolute velocity of P3. Okay, so anyway, that was a huge mouthful. This is very confusing, I understand. But hopefully you understand this. Okay, this guy is how to point to basically P2 or P3. It doesn't matter. They're coincident at this first instant. Okay, and then you take the derivative with respect to time to take the absolute velocity of P3, and you end up finding the velocity difference equation in here to get from there to VP2 to get the absolute velocity of P2, and then you have to add it to the apparent velocity of P3 with respect to 2, and that's the apparent velocity. So there's velocity difference equation here and apparent velocity stuff in there. Okay, but the bottom line, VP3 equals this. You can trust me with that. Okay. Okay, boy. Okay, so now. This is the most confusing thing in the whole course, this topic, as I said. So now what you do is you take, we simplify that just to make it visually clear. Now we're going to take the derivative of this, because really ultimately what we want to find is the acceleration of P3. So AP3, which means let's take the derivative of this with respect to time. Okay? And to do that, so AP3 is the derivative of this with respect to time. We're going to take the derivative of VC2, that's the velocity of C2 with respect to time, and that's AC2. Okay, and now we have to take the derivative of this stuff with respect to time. And notice this is across, so omega definitely changes. Okay, and rho doesn't, but un does too, and these things are both cross products. So if we're going to take the derivative of this with respect to time, we have to do the product rule, essentially. So we take negative the derivative of this, which is alpha, it's a vector, cross the normal one of that, okay, and then minus, because we've got, it would normally be plus, but we've got a minus sign there, the normal one of this cross the derivative of this with respect to time, and then we would just take the derivative of this with respect to time, and that's a vector, right? So you can see this is bold, okay? Okay, so very good. So now you've done the product rule, we've gotten the derivative of this, and things are getting even more complicated as we get into acceleration land. Okay, notice here that we're taking, there's a row in there we could pull up, but we're taking the derivative of un with respect to time, which we solved here. So we're going to take that, plug it in there, okay, and this is the derivative of vp3 with respect to time. That's a derivative of a vector is here, and we got all that. So we're going to plug this blue equation in there. We're going to plug the red equation in there. And check the math, put me on pause, look back at this, and trust me, when you plug all that in and schmooze stuff around and simplify, you get this huge, nasty equation down here, okay, which is what we're going to focus on. So everything we just did for this entire section was to derive this, which is, if you have this scenario of a link 3 moving on a slot on link 2 of any general slot, the acceleration of the point P3 on link 3 equals this stuff. Okay, now let's break this down because this isn't as complicated as you might think. Okay, first of all, I want you to note this entire thing in red here is the acceleration of P2. Okay, so think about it. This right here is essentially the acceleration difference equation, where we want to step from knowing an acceleration of c2 to the acceleration of p2 below p3 that's coincident with it, right? And so this may look familiar. You take the acceleration of c2, you plus it to, here we have the alpha cross negative rho un, which remember, negative rho un is a vector that points from c2 to p2. So that's the tangential component of acceleration, moving from that point to that point on link 2. And then check it out. We have omega cross, in brackets here, omega cross the same vector. So we have an omega, which of course is the angular velocity of link 2, cross the vector that points there, and then take omega cross that. And this is obviously the centripetal acceleration component of the equation here, of the acceleration difference equation. Okay, so again, if we're rotating, if this thing is essentially at that instant rotating, around c2, then we're stepping from that acceleration to that point, from that point to that point, we're trying to find the acceleration of p2, alpha p2. Remember, p2 is the point right below here at that first instant. We're moving from there to there. We use the acceleration difference equation and we get there. So you can simplify this whole thing down to just that. And you can just say, okay, if you know the acceleration of the point on link 2 directly below it, just use that. Okay? So that's good. We can simplify, you just basically throw all that out. That's what that all means. Okay, now we can see these two components here. Look at this. We have basically the speed of P3 relative with respect to 2. That's the apparent speed squared divided by rho. That should trigger to you, oh wow, that's a centripetal acceleration in the un direction. So that's the normal direction is 3 screams around this curve here. It's the acceleration of P3 relative, like in the normal direction relative with respect to 2. And then you have here the tangential acceleration as it goes around that curve in the ut direction. Okay, so you have the normal direction, you have the tangential direction, and these are both apparent stuff, meaning you're an ant on 2, nothing else is moving, for all you know 2 is not moving, and link 3 is moving around. You're finding the apparent acceleration, the normal centripetal component and the tangential component added together that's experienced by this, okay? So again, if from velocity land, if you have 2 bodies and they're moving on top of each other, and one is link 2, one's link 3, and they have 2 coincident points, P2 and P3, you take the velocity of P2 and you add it to the apparent velocity of p3 with respect to 2, and you get the absolute velocity